Welcome to week 4 of hazardous waste treatment and disposal. This week briefly covers the interesting property of how contaminants might separate when found in multi-phase situations, be it solid and water, two liquids, or even liquid and gas. A good understanding of topics covered in previous weeks will be very important this week. Let me start with some definitions. Partitioning is a general phenomenon which describes the tendency of a contaminant to exist at equilibrium between two phases. This concept is used to describe contaminants distributed between solids and water, contaminants distributed between water and air, and contaminants distributed between water and a biotic environment. Sorption is a specific partitioning and exchange phenomenon in which contaminants accumulate at the solid surface from the surrounding solution. Exchange is defined as the displacement of a charged species, such as a metal ion, by another species that has a higher affinity for the same site on the solid surface. This concept is utilized in analytical chemistry with the development of ion exchange chromatography, which is capable of separating and identifying ions like fluoride, chloride, nitrate, sodium, and lithium to the parts per trillion concentrations. Sorption is an equilibrium phenomenon in which hydrophobic compounds like organic hydrocarbons partition onto surfaces in a two-phase system containing a liquid, usually water, and a solid phase, such as soil or activated carbon. The physical process that occurs when a contaminant partitions onto a solid usually involves weak, reversible bonds between the contaminant and the solid. With hazardous compounds in a two-phase system, they can attach, sorb, and detach, desorb, repeatedly. This repeated and reversible process allows contaminants to move through a groundwater system or an activated carbon system, but at a slower rate than the water. Numerous mathematical formulas or graphs called isotherms have been developed to describe sorption. An isotherm is a plot of the extent to which sorption occurs at successively higher concentrations of sorbate at constant temperature. Isotherm plots provide a graphical representation of material sorbed as a function of the equilibrium concentration of sorbate. When a hazardous compound is released into the environment, it will partition onto subsurface solids or soils as water moves through the system. The degree to which the contaminant is distributed between the sorbed phase and the aqueous phase is described by the appropriate sorption isotherm for the compound and its concentration in the system. A general expression for contaminant sorption is called the soil distribution coefficient, and is defined as the mass of the contaminant sorbed divided by the mass of the contaminant dissolved at the aqueous phase. This soil distribution coefficient can be determined experimentally, which provides a very accurate measure of sorption in a solid water system. Because a contaminant must be in the bulk phase to be transported, the soil distribution coefficient serves as a basis for the relative contaminant velocity, which is quantitatively described by the retardation factor. The retardation factor provides an estimate of the velocity of groundwater relative to the velocity of the contaminant. Just as organic compounds are sorbed and retarded in soils, the rate of metals migration is usually slower than the rate of water movement due to bonding and partition processes on organic matter and the surfaces of other minerals. The partitioning of metals is highly complex and depends on a number of environmental and sorbent properties such as pH, cation exchange capacity, redox potential, iron oxide content, etc. Unlike the modeling of organic hazardous compounds, reliable compound-specific distribution coefficients have not been developed for metals partitioning. Volatilization is often called evaporation. Volatilization is the transfer of chemicals from solids or liquids to the gaseous phase. As you can imagine, depending on the contaminant and the site characteristics, volatilization can be an important mechanism for the loss of hazardous compounds from soils and liquid waste systems. Volatilization may decrease the concentration of the wastes at a site. However, from mass balance, contaminants will subsequently be found in the atmosphere. Therefore, air emissions from contaminated sites and hazardous waste management facilities may become hazardous air pollutants or toxic air pollutants and result in health effects. Volatilization can also be applied as a hazardous waste treatment process to clean up contaminated groundwater through air stripping or to remediate soils by soil vapor extraction. When hazardous waste volatilization is considered, the most significant class of contaminants is known as the volatile organic compounds, or VOC. The most common VOCs are halogenated and non-halogenated solvents. Heavy metals and inorganic nonmetals generally exhibit low volatilities. However, organometallic compounds behave much like organic compounds and can exhibit significant volatility. For example, microbes may transform arsenic into a more volatile methylated arsenic compound. In addition, dimethylmercury has a different volatility than elemental mercury.